All right, so welcome everybody on Zoom and here in the lecture hall. So today, I think we will simply continue with the previous topic, which was probabilistic information retrieval, which is, as I said already, on the master's level. So I have to warn you that things will maybe be a little bit more complicated, but that's okay. We'll work our way through the formulas and try to understand what's going on. Before we proceed, though, I would like to, as always, ask you a few questions to make sure that you understood what we've been doing. That's pretty much it. So I need to go here, share my screen. Here, and here we go. So here's the first question. Which one of these ratios did we not define as an evaluation measure? True positives over all return results, true positives over all relevance documents, true negatives over all non-return documents, or true negatives over all non-relevance documents. Three of them we give names to. One of these we didn't give any name. It doesn't mean it doesn't make sense, right? But it's just that it's really used. All right, so I see answers coming in. All right, shall we look? All right, so true negatives over all non-relevant documents. All right, so can you now tell me why this answer, the true negatives over all non-relevant documents, what is it called? Yes? Yes, that's specificity, exactly. So it's all the non-relevant documents, the ones you do not want to return, and we are computing among them the ones that we actually do not return. So that's specificity. Okay, let's go to true positives over all return results. Maybe Zoom, somebody in Zoom can tell us what this is called. True positives over the return results. You can write in the Zoom chat. Sensitivity, sensitivity, I think, is the one minus another one. We'll come back to that. Specificity, so specificity is the fourth one, right? It's the true negatives over all non-relevant documents, right? What is the true positives over the return results? No, whoops, it's totally fine to give wrong answer. You can give as many as you want with me. We are here to learn. Precision, yes, exactly. True positives over all return results is the precision. What about true positives over all relevant documents? Will it be Zoom or the lecture hall that wins on that one? Yes? Recall, yes, the lecture hall won. Almost a few seconds later came the answer from Zoom. So yes, this is recall. The true positives over the relevant documents. That's the recall. I think, because this one is less used, that the sensitivity is 1 minus recall, to be checked. It's a 1 minus. I think it's 1 minus recall. I'll confirm that. Okay, so let's go to another question. On probabilities, because we had to brush up, which of the following does not always apply? Some of them always apply. These are general laws of probabilities. Some of them do not. First, the sum of the probabilities of all elementary events must be 1. Second, each elementary event must have a probability of either 0 or 1. Third, a probability must always be positive. And fourth, the probabilities of elementary events must all be equal. 2 of them do not always apply. Sometimes, but not always. right? We're going to spend not too much time because this is really the 101. Let's see. Exactly. So you are correct. Where we have probabilities of only zeros and ones, this is a specific case, right? Actually, it means that it's the minimum entropy case where you have a certain event and everything else is not possible. And the fourth one is called uniform probability distribution, right? If you have n elements, then it's 1 over n. All right. Another one, also quick. Which of the following statements are true? So it's basically asking you about independent and disjoint, right? Linking that to sums and products. So 2 of these statements are true. Which ones? So if you look at the 8 answers, it's actually organized in a cube, 2 by 2 by 2, right? So it's either independent or disjoint, then it's either union or intersection, and then it's either product or sum, right? So you can also just imagine in your mind what is the definition of independent, then what's the definition of disjoint, and then you just look for the 2 answers. Right, 9 answers. 11. All right, let's start to see if it converges. We have 2 majorities. Still have an opportunity to change, 18 answers. And 20. All right, so indeed, independent means that the probability of the intersection is the product of the probabilities. And disjoint means the probability of the union is the sum of the respective probabilities. All right. I think that's all I wanted to ask you, at least for now. So now I'll come back to my slides. Then I'll have also, as we make progress in the lecture, I might have others. All right. And of course, we lost that. All right. Maybe this. So where did we leave? We had this probability 101, right, that we did last time. So I stopped on these random variable things. A lot of people use a lot of random variables in many cases to the point that they even drop or forget the omega space. Just like you drop the little wheels when you know how to ride a bicycle, right? But what's important that I come back to is the notation. We use the notation, the probability function of big X equals a specific value is a number. What's very important to understand here, very important, is that here, this is a random variable. A random variable is a function from the omega space to a target space. Here, this is a constant. It can also be a mathematical variable replacing a specific value, but this here is not a random variable. It's a possible value of a random variable. It's very important to distinguish between these 2 things. All right. So then, when we have random variables, we can start defining the probability, the joint probability of 2 random variables, right? The probability that big X takes the value X and big Y takes the value Y. This is one way of writing that down. And you immediately understand what this does when you look here. It's basically summing over all elementary events so that big X equals small x and big Y equals small y, which makes it, again, obvious that the big X and the big Y are random variables. And the small x and the small y are mathematical variables that replace a constant value. All right, is that clear? All right, so this is called the joint probability distribution. And it can also be written as P of big X equals small x and big Y equals small y. That's an alternate notation. Actually, that's the one I might use during the lecture. And another thing you can define is the conditional probability of a random variable condition on another random variable. We already did for events, right? But now we do it for random variables. Now, mind the notation. The conditional probability of two random variables takes two parameters, two actual values, the value of x and the value of y. So this is really a function with two parameters. And here we index that function with x condition of y on y to make clear that we are defining the conditional of big X equals small x, given that big Y equals small y. And this is, of course, defined as the event. So it's the probability that both take this value, small x and small y, divided by the probability that big Y is small y. This is not surprising. That's exactly the same definition that we took for events. If you consider that big X equals small x is an event, and big Y equals small y is an event, then this matches the probability, the conditional probability of these events. Okay. In practice, though, even though this is formally one of the notations, I will rather use that notation because I think this is probably easier to parse, right? Who finds this easier? Who finds this easier? Maybe less of you, right? So this is why I'll stick to this notation. But you should know that this notation exists too. Okay, and now yet another one of my big warnings. Do not ever, 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 ever write this. Forbidden. This here is something that is, let's call it approximate. You kind of know what this is doing because, okay, you see small x, that's probably random variable big X. Small y is probably random variable big Y. But as soon as you start replacing, do it in your mind. Replace x with an actual value and y with an actual value. Let's say, okay, what's the probability of one condition on two? And then you realize that doesn't make any sense. Do not do that. Okay, and sadly, I have to add, this is done everywhere in plenty of textbooks, including the textbook we use in that lecture. But since I'm going to drive you to all that with the actual accurate notation, I'm pretty sure it will be very easy for you to then rectify or transform it back in your mind to the actual thing that it should be. All right. Having said that, now we go back to information retrieval. So what did we do? So I'm assuming here, I'm going to give you a bit of background context. We assume that we have a collection of documents and information needs, and we use a few people, or we do it in our minds, but we ask a few people, if I give you that document and I give you that information need, then this person here is going to tell you whether the document that you gave them corresponds or use relevance to the information need, or is not, right? So it can be a no, or it can be a yes, right? Yes, no. This was done actually in practice back to the 60s, I think, with the Cranfield data set. We didn't have so many computers back then, so you see the number is quite small, but nevertheless, we managed to get these relevance judgments. This is what is called for every combination of document and information need. Later, we did the same with the Trek data set, which has almost 2 million documents and 450 information needs. And the same, we asked domain experts to give relevance judgment. It was often in the field of aeronautics back then, because I guess this was a good use case for information retrieval, or maybe they needed information retrieval as well. All right. But how do we interpret that now with a probability space? Here's the thing. Imagine that we had, that's of course a thought experiment because that's not true. Imagine that the population on Earth would be quadrillions of people, quintillions, like a huge number of people. And imagine that we want to give them like billions of documents and millions of information needs, for example. And we want to even give sometimes the same combination of document and information need to like 1 million different people. Of course, it's a luxury, right? If you have quintillions of people, it's kind of easy to do, right? So imagine we do that, and every time we give one person a combination of a document and information need, and that person answers with yes or no, it's relevant or it's not relevant, this gives us an elementary event in an omega set, all right? So if now we go to the quintillions, that means that the omega set is absolutely gigantic, right? It has quintillions of events in there. And every one of these dots like this gives you one document, one information need, and that also includes the query that that person used to model their information need, and one red flag. So what's important is every dot here is deterministic, right? That's what an elementary event is always that way. If you have one elementary event, you know exactly what document, what query, and what red flag that is. Right? Okay, so of course we have lots of queries, lots of documents, lots of domain experts, and this is only a thought experiment because, of course, as you can imagine, we cannot actually do it. But the nice thing about doing science is that we can do thought experiments, right? It's like Schrödinger with the cat. Of course, it's nice that he didn't actually do that, but this was a thought experiment that was useful to the advancement of quantum physics, right? Okay, so let's imagine we have these quintillions of people. Okay, so what did I mean when I said for each elementary event, I have one specific document, one specific query, and one specific red flag? Well, even though I didn't yet call it that way, we actually defined the random variable. Because what we are saying is that this elementary event maybe was associated with the query information. Then we can consider that a random variable Q maps every elementary event to a query, right? And this specific elementary event is mapped to that specific query. But in fact, it's a random variable. It maps every single elementary event to a query. And of course, maybe 1 million different elementary events will be mapped to the same query, right? Like any random variable, just like our blue squares and so on. All right? So from now on, in this course, I'm going to be using Q. Big Q, I always use the uppercase for the random variables, lowercase for the mathematical variables. Big Q, uppercase Q, is a random variable that is a query, right? Then we have big D, which is also a random variable. And this big D gives us a document. So for example, for this very specific elementary event, maybe that the document that it is associated with was the information retrieval book, right? Maybe it's the same event, right? So that was the query information, and that was the information retrieval book. So this is also a random variable that we call big D. And finally, we have another random variable called big R, that is the flag, right? So it's a Boolean, and in that case, it was yes, well, of course, because in that specific case, we had the query information and the book information retrieval. So yes, it's relevant, right? But we have that, of course, a quintillion times. But of course, when I define the random variable, it's not just for an elementary event, it's for all of them, right? So these big D, big Q, and big R are defined on the entire omega space. Right? Okay. And the beauty of having defined these random variables, R, Q, and D, is that now I can start writing down formulas that are probabilistic formulas, and I can even interpret them, right? So this here is the probability that, conditioned on the fact that I gave a domain expert document D specifically and query Q specifically, the probability that that domain expert said, yes, this is relevant. All right? So be very careful. This is a random variable. This is an actual possible value of that random variable. This is a random variable, and this is 1 or 0. All right? So the probability of relevance conditioned on the fact that the document was small d and the query was small q. Of course, it's possible to draw now the entire omega set in this way, where, of course, now I nicely arranged all the documents D here and the query right there. And of course, there's a lot outside of that, right? But basically, I intersect the two because this is an and here. So I intersect document D query Q, and then I look inside what's the ratio, what is the probability that it's relevant. So maybe these domain experts found it relevant, and these didn't. So that gives us a probability. Is that clear for now? All right. So now, in an ideal world, the domain expert will agree, right? That would be best, right? If I give a document that's relevant to a query, you would kind of expect that this is an objective statement, right? There is a consensus in the community of domain experts. So in the best case that there is a consensus in the community, then if I give you a document, so here it's D and Q, they will all agree that D is relevant to Q. Maybe they will all agree that E is relevant to Q. Maybe they will all agree that F is not relevant to Q. And they will all agree that G is not relevant to Q. So this is the case where they all agree there is a consensus. However, this is not how science works. There is, of course, a consensus, but there can also be disagreements, right? So in practice, maybe they will not all agree, and you will get a specific probability, so that's depending on this domain expert, of relevance for these 4 documents, D, E, F, and G. So now here's my question. Given this information, which are the probabilities of relevance of these documents, D, E, F, and G, and I have query Q now in my system that is incoming, what documents should be returned in what order? Given this information by the domain experts. On Zoom, anybody? What's the document you should return first? Yes? Yeah, so that would be. Absolutely, yes. So we'll talk about the cutoff value. Let's say it's ranked retrieval, right? So ranked retrieval works by just going down. It's the user basically that decides on the cutoff, right? You go to Google, you get the first 10, then the users can click and see the next 10, right? But the cutoff is nevertheless important. I'll come back to that. So in that case, what document do you return first?
So Zoom says highest probability first.
Yeah, which one? D, E, F, or G? Yes? F, exactly. F, and then D, and then G, and then exactly, I sorted them here. So you see, we just sort by descending probability. This here is called the PRP, Probability Ranking Principle. It's the idea that you return first the documents that have the highest probability of relevance against your query. It's really a principle, and one of the inventors of this probabilistic information retrieval that we are studying here basically had this founding explanation where he was saying that ideally, if we are able to compute these probabilities extremely accurately, then this is the ideal information retrieval system. It should return, according to this principle, the documents by decreasing probability of relevance against the query, which is exactly what we are doing here. All right, so now, and I'm coming back to your comment about the cutoff, if what we are doing is not ranked retrieval, but Boolean retrieval, in the sense that either you return or you don't return, then it's natural to kind of say, okay, I'm going to return a document if it's more likely to be relevant than it is likely to be irrelevant, right? So this here gives us a cutoff value of 0.5, exactly. So here I even have the display that here it's more relevant, here it's more irrelevant. And indeed, this is equivalent, so this thing here is equivalent to saying that this is more than half of probability, right? So this is it. So you basically have this slider here for this value there, and you put a cutoff at 1/2 for your Boolean querying system. So you see, we can even derive a Boolean querying system, not just a ranked retrieval system. All right, in the book, you will even find some extension of that with weights based on costs that you can even weight and then put the slider at a different place if you want. Basically, if you want to not use 1/2 but put the slider somewhere else, it would have to do with how bad is it if you have a false negative or a false positive. Because maybe you care a lot about not having false positives, but you don't mind so much about false negatives, right? Or the other way around, in which case you would put the slider maybe at another place. And then we are back to the ROC curve, right? This metal detector, where you have the knob that you adjust. All right. So now that we are done with that, what is the difficult part right here? If you build a system, what would be missing? Can you build a system that does that? Well, you would have to compute the probability, right? That's the challenging part. How do we compute this probability? And this is exactly what we are going to study now with what's called the binary independence model. That is one of the founding models that gives you a way to compute these probabilities. And as you can imagine, we are going to do that with the Bayesian rules and everything that we've been rehearsing last week and this week. Okay, so back to the model and abstraction. We have a document. This document is a list of words in its raw state. We simplified it to a set of words that gave us a vector of Booleans. This is what we did for the Boolean retrieval system, right? In the case of ranked retrieval, we moved to a bag of words. And here, that was a vector of numbers, right? This is what we did with the vector space model. Well, I have good news. This week, we are going to keep it simple. And so we are back to this simplified assumption of a set of words with just ones and zeros. Makes it easier, right? So we don't have here term frequencies or anything. We just consider that a document can contain or not contain a term, and that's it, without anything else. So we have the same abstraction as for Boolean retrieval. And yet we are going to be able to derive a ranked retrieval system. How cool is that? Okay, so that means that our documents and queries are actually vectors like this. So this assumes that there is a specific indexing of the terms, right? So we know exactly what term is in what position. And then we have Booleans in a document vector, and we have Booleans in a query vector. That means if we assume that model, that we can kind of decompose the D random variable, big D and big Q, we can decompose them into their coordinates. It means that we can use the subscript. So for example, D ETH is a random variable that says whether or not the document contains the word ETH, the term ETH. This has the advantage that according to our model right here, this is a Boolean. So this random variable right here, DETH, is a Boolean. It's either 1 or 0, right? Let me remove the chat box to make sure that also in the lecture hall you see the screen. Okay, and I do the same for the query because the query is also a vector of Booleans. So if I look at the coordinates of my vector of Booleans, I can define also a query random variable that is Boolean for every term. And for every term, Q subscript information returns 0 or 1. And basically, if you look at big D or big Q without subscripts, it's a random variable that takes value into the set of vectors of Booleans, right? All right, so small d and small q are vectors of Booleans, and big D and big Q are random variables. Is that clear for you now, this difference, uppercase, lowercase, random variables, and so on? Okay, so now, once we are done with that, we can start writing things like this. What is the interpretation of that formula? Can anybody tell me in plain English what this means? Anybody? on Zoom, maybe? The chat. Can anybody tell me in English what this is the probability of? Imagine I give you a specific Boolean. I call it dk. So this is a mathematical variable, right? So this is either 1 or 0. And q is a query. So that's a vector of Booleans, small q. So how do you interpret that? Given a value for dk and a value for small q. Yes? Yeah. Exactly. Yeah. Indeed. So I'm repeating for the people on Zoom. This is the probability that the document contains or does not contain, depending if this is 1 or 0, the term k, given that this is query small q, and the document was relevant to the query according to the domain expert. Right? It's almost what you said, just reformulated it a bit, but that's basically you said. The probability, let's say this is a 1. Then in that case, it's the probability that the document contains term k, that it was relevant, and that the query was q, small q. Okay, and I wrote it here again for you too. Okay. By the way, here, I assume I took a shortcut. I should actually fix that. Here, when I say that the document contains term k, I really mean if this is 1. So I'll actually fix that maybe to make it clear. Because if this is 0 here, if that is a 0, then it's a probability that it does not contain term k. Right. So I'll fix that slide. Can we maybe make a note, Abhishek, that I don't forget? I'll fix that slide. Okay. So now we are making an assumption on the way that this Boolean random variable will work. That is also called the naive Bayes assumption. It's a simplifying assumption that helps us compute things in a simpler way. So we are going to assume that the terms occur independently in the documents. Independently, what does that mean? Well, in probabilities, that's a product, right? Independent product. I asked you the questions, right? Just at the beginning of the lecture. So it means that we can decompose the probability that the document is this specific vector of Boolean small d. We can express it as the product over all the terms that the document contains or does not contain term k. And where do we get that it contains it or not? From the original vector, right? So imagine that in this vector d, for k equals 1, we have a 1, and for k equals 2, we have a 2. Sorry, I rewind. If for k equals 1, we have a 1, and for k equals 2, we have a 0, it means that the first two Booleans are 1 and 0. Then we are going to have the probability that d1 equals 1 multiplied by the probability that d2 equals 0, right? So I just pick all my Booleans in that specific vector, their coordinates, and I just multiply all of these, right? Let me to be absolutely sure that this is clear. Let me assume that the terms are, I don't know, information, retrieval, ETH Zurich. So I have just 4 terms. Information, retrieval, ETH Zurich. Now, I have a document that just says information ETH. What vector is that? 1, 0, 1, 0, right? Information is in there, retrieval is not, ETH is in there, Zurich is not. So this small d would be 1, 0, 1, 0. What does this mean? Well, this means that's the probability that d information equals 1 multiplied with the probability that d retrieval equals 0 multiplied with the probability that DETH equals 1, multiplied with the probability that D Zurich equals 0, right? I really here hard code the ones and zeros from the document that I'm testing, right? This is a simplifying assumption because this is really an assumption of independence. What this is saying is that these random variables, dk, are independent from each other, and this is why I can just multiply, right? Is that clear? All right, so this is called the naive Bayes assumption. And you'll see that it comes very handy because it satisfies a lot of things. Do we have a question on Zoom?
Yes. If ETH occurs, it is probably more likely that also Zurich appears, no?
Yeah, you're absolutely correct. So of course, this is a simplifying assumption, and it can be criticized. You can, of course, argue that this assumption does not hold in practice. It's an approximation. So we approximate reality by simplifying in that way. But I absolutely agree with you that it can be criticized, and you could also build a system in which you do not assume the independence. In fact, it's something that is done. It's even explained in the book. If you look at the end of the chapter on probabilistic information retrieval, you will find the commentary on that. I think they use trees of terms in order to model this. So you're absolutely right to be critical of this assumption, and this is a perfectly valid argument against that assumption, right? So it's really something that should be taken as an assumption, right? Did it answer your question?
Yes.
All right, perfect. Okay, well, this is the same, in physics, if you assume that at low speeds, time is the same for everybody, that's also an assumption, right? And we know that at very high speed, it's actually not true. All right, so the terms occur independently in the documents. Now, let's come back to what we wanted to do. We wanted to compute these probabilities right here because we want to rank them. We want to just rank them, and that gives us the documents that we need to return. Okay, so what we want to compute is a conditional probability, right? We need to compute the probability of relevance given a specific document and query. It's very hard to compute the probability of relevance given a document and query, right? But it's pretty much like when I ask, what's the probability that it's raining outside given that I have my umbrella, right? And so we saw that when we have a conditional probability that's hard to compute, we just use this magical formula called Bayes, and we just swap the two sides, right? This is what we love to do, so let's do it. Let's swap the two sides. So this formula right here, computing the probability that it's relevant given the document D, is the swap, so the probability that is document D conditioned on the relevance, and then of course you have these Bayes formula things that basically do the transformation. Here I just wrote it with just D and R because I wanted to remind you of the Bayes formula, right? So this is why I only put R and D. But you agree that this is the Bayes formula, right? This is exactly the Bayes formula. Okay, now let's just add Q, because actually I can add, I'm absolutely free to add whenever I want the Bayes formula. I'm free to add the same condition everywhere and it still works, right? You just need to think about it. You're basically just taking a subset of omega when you do that, where Q equals small q. So I'm just taking this formula right there and adding everywhere, right here, right here, right here, and right here, that we are looking at query small q. Okay? And now I have this, in order to compute this, which is very hard given that order, I'm turning it the other way around with these correcting factors. So in other words, now we are going to compute the probability that we are looking at document small d, given that query is small q and that the document small d is relevant against q. All right? And plus we have to correct with these two little things there. All right, so now I have a question for you. How can we simplify this formula? And of course, this is what we are going to spend the rest of today doing. We are going to work our way through this formula. Can we get rid of some of it? And now I'm going back to Clicker in order to see what ideas you have. All right, so tell me, this is the formula we are looking at. Is there any low-hanging fruits to simplify this formula? So maybe there's none. Maybe we simply divide everything with q equals small q. Very tempting, right? Druck nur auf die Klinke die Türe springt dann auf, or computing the odds of the prior and posterior instead of the probabilities will get rid of the denominator. So what do you say? Will you like the oh, some of you are pessimistic. All right. The third one is Rotkäppchen, right? In German. Is it what it's called? Rotkäppchen? It's a fairy tale. Okay, anyway. This last one is the correct answer. Computing the odds, indeed, is the way we are going to do it. Okay, let me come back to the slides. And normally I prepare the set of slides that starts exactly where we want to be. Oh, that's strange. Zoom is behaving strangely today. Okay. All right. So here's what we're gonna do. We want to compute the odds. How do we compute the odds? We take 1 and we take 0, right? It's just the complement of the probability, right? So this is the probability that it's relevant, the probability it's irrelevant. I just wrote the same thing, but just, now it's a 0 here, but it's pretty much the same thing. How do I take the odd? I just divide this divided by that. So I get the odds that r equals 1, just the division of that by that. And now I divide, where is that? Sorry, I didn't divide yet. I just wrote down the formula of the odds. So the formula of the odds is the probability of relevance of that divided by the probability that it's not relevant. Now I take this and replace it with this, and I take that and I replace it with that. This is what we get. What happened here? Well, the denominator was lost. Why? It's the same here and here. It's the same denominator. Yay, we got rid of the denominator. That's one of the three, right? So we had 1, 2, 3 factors. Now we managed to get rid of the denominator. So that's really nice, right? That goes away. All right. And now we have this formula right here. I can rewrite it slightly like this. What is this? Okay, then I'm going to ask you on clicker. Tell me. I think it's going to ring. So it might be that you'll have to wait until the break to actually know the answer. We'll see. If you are quick, you get it before the break. Otherwise, there is a big cliffhanger for season 2 of today's lecture. Okay, then you'll know in 15 minutes. So enjoy your break, and I'll see you in 15 minutes for the continuation of this. Thank you.